CPU performance of supercomputers has been improved toward exaflops. However, the speed of storage performance improvement is slow, and the performance gap between CPU and storage is growing wider and wider. The performance improvement of most applications is limited. To fill the gap, an innovation in computer systems is required. This research aims toward that innovation. The storage system in supercomputers is installed at a separate place from compute nodes. This prevents storage performance improvement. We suggest moving the storage system toward compute nodes and installing it in compute nodes. Applications access near data. When increasing the number of compute nodes, the access performance is scaled out. Distributed metadata servers that manage distributed data locations cope with the increase of the number of compute nodes.
The most critical problem in supercomputers is storage, because the performance gap between CPU and storage is wider and wider. Our solution is Node Local Distributed Storage System. Access performance can be scaled out by exploiting local access. Metadata servers manage file locations. The performance of metadata server is critical for a file system to scale out when increasing the number of compute nodes. It is not easy, but we solve this issue and design a scale-out distributed metadata servers.
Metadata servers hierarchically manage files using directories. How to manage the hierarchical namespace using multiple metadata servers is a critical issue to supporting millions of compute nodes. Each file is managed using a directory identifier and file name, which is distributed among multiple metadata servers. This design enables processing balanced operations among multiple metadata servers, not only concentrating on a particular server. When increasing the number of compute nodes, distributed metadata servers can support them by increasing the number of metadata servers. We developed a prototype system of distributed metadata servers based on the design. For large-scale environment, we evaluated the performance using a discrete event simulator. This graph shows the number of operations in a second when increasing the number of servers. It achieves 28.5 million operations in a second when using 1,024 servers.
On a supercomputer, the execution of applications is disturbed by operations of system programs such as the management of memory and storage. As the number of computation nodes increase, the application performance is more degraded by such disturbing operations. So, we developed a method to minimize the effect of such disturbing operations.
Applications on compute nodes use memory to load computation data and the cache of storage data. When the memory becomes full, some memory blocks must be released. Our method releases a small amount of memory if the memory is mainly used for computation data. It contributes to a high application performance. In some cases, the memory is mainly filled with the cache of storage data. In these cases, our method intelligently determines the release of large amounts of memory at one time, which greatly reduces the frequency of memory release operations and contributes to a stable application performance. Our experiments using a weather forecast application showed that our method minimized the effect of disturbing operations.
The execution of applications using many compute nodes is accompanied by data transfer between compute nodes. However, the data transfer is one of the factors that impede scalable performance improvement. So we designed a new scheduling method that minimizes data transfer based on a graph of file I/O dependency.
This graph shows the dependency of file I/O in an application. Each circle represents a task. In a naive method, tasks are allocated to compute nodes in order. Each color represents a compute node. With this assignment, there are many arrows connecting tasks with different colors. In other words, there are many data transfers between compute nodes. Our new method minimizes the number of the arrows connecting different colors. This approach reduces data transfer between compute nodes down to 14% and reduces execution time by 31%. The research outcome is included in the GFarm file system and the Prake workflow system. They are available online. The GFarm file system has had 19,000 downloads from 79 countries, and the Prake workflow system has had 14,500 downloads. We have 3 research groups for each topic. The File System Group, the Compute Node OS Group, the Runtime System Group. We established a non-profit organization, Tsukuba OSS Technical Support Center, to technically support the GFarm file system and the Prake workflow system for production use. The GFarm file system is practically used by HPCI Shared Storage led by the Ministry of Education, Culture, Sports, Science, and Technology. It is also commercially used by companies. In addition, SNIA-J Extreme Storage Study Group was established to promote HPC storage in the storage industry. It is our goal to continue further research and development and to contribute to big data analysis in supercomputers.